lines in three-dimensional space. Before I talk about a straight line in three-dimensional space, let me talk about a curve in 3D space. And I'll draw one, just something representative, something like that. Now, maybe we have a function of sorts that would describe this curve in 3D space. Like maybe there's some sort of z equals f of xy that would describe this, at least on a limited domain perhaps. But another way to describe a curve like this in three-dimensional space is by thinking about it being the end position of a bunch of vectors that start at the origin. Something like this, that point to the curve itself. And I could draw a whole bunch of vectors like that that would land on this curve. So instead of defining it in terms kind of a standard way of defining functions, maybe we could define a curve or a line, as we're about to do, in terms of vectors. So let's draw a line, just kind of random line in space. We'll call that line L. And let's say we have a point P naught, which is on the line. And let's consider a vector V, which is parallel to line L. So I'm going to draw it a little bit below to start. So I'll just draw a small vector V, which is supposed to be parallel to line L. Now I'm also going to draw a vector from the origin to the point P naught, and I'm going to call that vector R naught. So it's like a starting position. Now, if I wanted to draw the vector R naught plus 0v, that's of course the point P naught, or it points to the point P naught. What if I wanted to draw the vector R naught plus 1v? Well, if you recall how we add vectors, I can move my vector v to the end of R naught and draw it right about there like that. Then the vector R naught plus 1v would exactly be this vector, which points to that position on the line. And if I wanted to draw the vector R naught plus 2v, so I have 1v, then I'm going to draw another v right at the end of the first v. Let me change those colors, see if red will show up. So here's my 1v, and here's my 2v, like that. And if I want to draw the vector R naught plus 2v, that would be the vector that starts at the origin and points to another point, which also is on the line. And then I could do R naught plus 3v plus 4v. But the point is, this is a way, or this is the idea of getting a way to draw a line and thus getting the equation of a line using vectors. So an equation of the line using vectors in three-dimensional space, or even more dimensions, but we're doing three-dimensional, would be R, the vector R, equals the starting vector R naught plus some t times a vector v, where v is parallel to our line. And note that t is any real number. In fact, t is going to be all of our real numbers to get the entire line. So here's how we usually write. Let's do a little more detail. If R naught is the vector, say x naught, y naught, z naught, a starting point, and we'll say v is some vector ABC, again, which is parallel to our line L. then the vector r, which is going to describe the line, will be the vector x naught plus t times a, and then y naught plus t times b, and then z naught plus t times c. So you can almost think of this line in the following way, where we have a starting point, x naught, y naught, z naught, and then we can take each component separately. We have parameterized our equation. And you can think of a, b, and c sort of as being respective slopes in x, y, and z. That helps me think of it sometimes when I'm doing problems. So let's do an example to make it a little more concrete. So let's find a vector equation of the line which goes through the point 5, 1, 3, and is parallel to the vector I plus 4j minus 2k. And then we're going to find another point on the line. So it's pretty simple once you get used to it. This is going to be my starting point, x naught, y naught, z naught, 5, 1, 3. And then my vector v will be the vector 1, 4, negative 2. And so the equation of my line, and I'll call it r of t because it's going to be a function of t, is going to be the vector equation 5, my starting x, plus 1t, and then 1, my starting y, plus 4t, and then 3, my starting z, minus 2t. And there's the vector equation of a line. Now let's find any other point on the line. So we can plug in any value for t that we want. We already know what it is when t equals 0, so let's find r at 1. So all I'm going to do is plug in 1 for every t. So I get 5 plus 1, 1 plus 4 times 1, 3 minus 2 times 1, and we have another point on the line.